Good morning. Good morning, everyone. Welcome to the AskHilti webinar about structural strengthening with concrete overlay. And I am today's speaker, Terry Zhang. I am the Regional Engineering Marketing Manager for Hilti Northern Europe. I look after concrete-to-concrete type of connections, such as pull-install rebar, punching shear, and concrete overlay, from code and approval perspective to software, services, and technical product. I also take care of the Hilti on testing services. I have been with the company for 9 years and have been in multiple roles and organizations. I have worked in field engineering role, product development role in headquarter, and I am right now in Manchester, our Northern Europe headquarter for engineering marketing. So today, in this webinar, we will cover what is concrete overlay, where can it be used, the design method, the new AOTA TR66 for pull-install connector design. I will also at the end share with you the Hilti concrete overlay portfolio. So I see now questions that you can't hear my voice, right? Can anyone else confirm that you can hear my voice? I will have to check the setting. Is this something on my side or something on your side? Okay. Yep. Thank you. I guess yeah, my audio works fine. So if you can't hear me, then probably is your audio device on something happened on your side. And also, by the way, the handout is put already in this platform. If you click the three dot with the apps there, then you can see the handouts and then you can download it right now or after the call. And here, I also welcome you to put those questions that you might have during the call there. Then we might take it right after the call, or we can also email you back with the answer afterwards. Also, it will be highly appreciated if you can take part in the polls to let us know whether you want to receive some update from us in the future, or do you want us to get in touch if you have any questions regarding like rebar design or concrete overlay design, then we can get in touch. So let's get back to the presentations. So when we are strengthening the existing concrete structure by adding a new concrete layer to the existing member, it is very important that we ensure a monolithic or composite behavior of the concrete cast at different times. It can be achieved by dialing the shear interface and transmitting the tensile force generated by frictions into the shear interface. Concrete overlay is becoming increasingly important due to the growing need for repair work and reinforcement of the existing structure. If the shear stresses in the bonded joint between the concrete layers that were put in different times are not sufficiently transferred, the structure actually the safety is at risk. So having said that, let's take a closer look to why a shear connector is needed. So just imagine right now here, this is a beam. When we load the beam with a force, the beam will definitely make a certain deformations. And we will have two forces on the support side, which is on the left and on the right, to keep the beam to stay in place, so-called the equilibrium state. I mean, this force has to go to the support, but the force can't go directly to the support itself. So the force will go down the beam, up and down, up and down, up and down, instead of punching through the concrete and until it reach the end to the support. I mean, green arrow here is representing the shear load. I mean, shear load tend to fracture the beam. And in this case, we can represent it in a diagram, the shear load over the beam. I can hear some song asking questions. Is it okay? Yep, and just checking the audio part, so make sure that you hear my voice. So yep, so this is um, a typical, let's say how the let's say structural engineer, let's say, analyze the beam, right? I mean, and usually then later on it's also being converted into these diagram, the shear load over the beam. I mean, usually is it also represented in a struct and time model, compressive in the blue side. I mean the green is the shear. So just imagine now, what if we cut the beam into two parts? First, you see the deformations. The upper part actually tends to extend beyond the lower part, which is pointed out by the red arrow on the extreme end of the beam. Um, so actually, I mean, only the lower part of the beam is working as a load carrying member, and the upper part is actually just purely adding load to the lower part. And this is actually weaker than a full beam if we cut, let's say, the beam into two parts, which is actually try to mimic what the concrete overlay will work without the shear connector. But then that's why we need a shear connector in the overlay application. We actually bring back, let's say, these additional deformations and make the beam work as a whole, as one section again, to ensure the monolithic behavior. And this is the working function of the shear connector in the concrete overlay. As you can see here, then highlighting the shear connector, how it works. Again, is bring back as a whole beam performance. So what the connector is doing in principle, you can see here, the low, again, the upper part of the concrete want to extend to the outside, pushing the shear connector on the new concrete layer. The lower part of the concrete layer is actually pushing inside. The connector help actually transfer the load between the two layers. Concrete overlay is a typical application. You can find it in the building constructions, industrial industry, or civil engineering. I mean, for example, in the industrial segment, you might look into ways to strengthen the floor because there's like a new production process with heavy machinery, or in a civil project like in bridges, that there is the need on the structure, that the structural capacity has to be higher. I mean, because there is change of regulations, or let's say, you're widening the bridge and then you need to take a higher load, and then here you also need to look into the way to strengthen the bridge, and one of the options is by the concrete overlay. So the first part, I mean, talk about why you need the overlay, right? Again, to bring back the monolithic behavior of the structure, and we can also use it in the civil engineering or in the building constructions. So now we will move to the second part of today's presentation, which is about the design method, the new aorta TR66, and the I will also show you what is the difference comparing to what is the existing one, which is the EC2 part one and part two. So when we go to the regulation part, we in for new construction, then we have the EN 1992, part one and part two, for example, for bridges, and then there's a section about concrete overlay. In EC2, I mean, the difference is, I mean, the anchorage is assumed in yield, and that is not actually the case for install shear connector. That's why in the renovation project or refurbishment project, I mean, we in the past, then we have the FIB model code 2010, and later on it is now fully under the AOTA, the European standard for concrete overlay design, which is the method so-called TL66. Um, we it is first published in 2019 with static and fatigue design, and later on in 2020 it got the first amendment, including the seismic design. And today we will be mainly focusing on the TL66 design method. I mean, the TL66 design method, I mean, is the first time actually regulating the concrete overlay in existing buildings. This is the European design method. In addition to EC2, it is the safest, officially recognized, and also the most economical solutions. It has a very clear procedures how to design static case, seismic case, and fatigue case. It is very important also to point out here that the product to be designed according to this design method, TR66, has to be assessed by the European Assessment Document, the EAD 332347. It is not like the normal EAD for chemical anchoring or polyester rebar assessment. So a product carrying such European Technical Assessment, ETA, or well known as the product approval for standard anchoring or standard polyester rebar, are not fit for concrete overlay unless they have been assessed in this very specific EAD 332347. Then they are fit for concrete overlay use. They also can be designed according to this technical report TL66. Um, Now bring a bit more, let's say, the whole regulatory framework of the concrete overlay. As mentioned, the new Tier 66 cover static, fatigue, and seismic, and it cover actually only the header stuck. Um, it doesn't include the band rebar or the hook rebar. So for that, Hilti actually offer the Hilti design method for hook rebar for the same applications. um, and today we will not cover actually that hooked rebar part. We might cover that in the future webinar. So if you're interested, drop some comment there and let us know, and then we can arrange next one. But today we are mainly focusing on the TR66 on that one. So let's now take a deeper look on the TR66. In TR66, there are actually two types of forces acting on the system being considered and calculated. I mean, they are the external forces, number one. Number two is the forces resulting from restraint at the perimeter due to concrete shrinkage. I mean, these forces activate the tensile force perpendicular to the interface, which are carried out by the connectors and transfer into two concrete layers. As you can see here, again, we have the shear load on top and later on converting in shear stress. And here, it is actually, according to code, it is allowed to subdivide the interface into zones to contribute to different shear stress. It is not allowed to redistribute the stress for rough or very rough surface. And here, I mean, the maximum value of each zone is decisive. That's why this is the way, let's say, we optimize the design. The where the shear stress is higher, then we will have more connector. Um, And as said that, I mean, so we have to, let's say, subdivide it into zone for design, but also very important for you to understand, according to the design method, there are two design flow. And one design flow is calculating or taking care of the external forces, which is mainly, for example, if we're considering a slab strengthening case, and then the central area is mainly taking the external force. And when we move forward to the edge area, which is along the perimeters, we will also need to take care the external force and additional the restraint force, so-called the concrete shrinkage or the cracking force. So let's now focus on the first design flow, which is taking care about the external load. So this is then the goal in this part, which is the verification, verifying whether the shear stress is equal or below the shear resistance that the system can take, so that this is a safe design. To do so, first we will need to convert the shear load into shear stress. So the shear load is for example here the VED divided by the cross sectional area, which is a Z times BI. In this case, BI is the width of the concrete, and then the Z is the inner level arm of the composed sections. So simply, I mean, load divided by area, then you get the shear stress. And actually within the TR66, it gives two options. If the interface is having a very strong adhesive bond, you might not need to use a shear connector. And then you can calculate, for example, here, the tau RD, which is the resistance of the system. Then you can calculate it even without a shear connector. It allows you to do so if the bond is strong. If not, if the bond is weak, and then you will need to use a shear connector. And then to calculate the shear resistance of the whole system is a much longer formula. And then, I mean, we will cover it in the later part to show you what the formula is about. But again, ultimately here, the goal is to see whether the shear stress applied into the structure can be taken up by the shear resistance provided by these option 1 or option 2 formula. So now we go deeper into these formula, and then here, I mean, for example, show you also the formula coming from the EN 1992, which is then the formula for shear connector, mainly for semi-precast concrete, and then the formula below, which is the same formula as you see in the previous page, which is the formula coming from AOTA TR66 for pre-install shear connector. So if we take a look here, then the strength of the concrete to concrete interface is like a combination of several components. So the red one here, for example, representing the aggregate interlocking between the new and existing concrete, it will develop this interlocking function and holding the two sides of interface together. And then the blue one, which is the shear frictions. Since the interface is not perfectly smooth, the in the two slides of in the two sides of the interface. And due to the lateral displacement, it will detach from each other and thereby load the connector in tension. Which later on, this tension of the connector also transfer and create a compression and frictions between the two layers. And the one in purple color is a dial action, which is the interface shear load will apply the shear load on the connector. And this results in a small lateral displacement and thereby bending the dial. That's why we call it the dial action. And ultimately, then we have that green, which is like the limiting factor, the concrete struck resistance. So the shear load will go through the interface as compression in the concrete, and this is where the maximum actually the system can take. Um, and here, so as I highlight here, you will be able to see the two formula actually. They are not definitely they are not the same, but they share a very high similarity. The differences is mainly in the EC2 design method. As you can see here, we highlight the FYD, which is the yield strength of the rebar, is being considered, while in the AOTA TR66 method, we highlighted the sigma S, which is the stress area of the shear connector of the relevant failure mode that is being considered. So that is the main differences. But then you might have the questions. As you can see, I put two application picture on the right hand side. One is like the concrete overlay for semi-precast application, and another one in the bottom one, which is the concrete overlay for breach decking. So why can't the two application be designed by the same EC2 method? They share definitely similarity. Why can't we use the EC2 method for everything? The reason we can't do that is simply because, in the first application, these kind of semi-precast type of connections, the transfer reinforcement that is installed before any concrete is cast, it will be perfectly anchored with the horizontal reinforcement. Thus, when the reinforcement is put under tension, the only possible mode of failure is yielding. But for point shear connector, it can't be anchored into the horizontal reinforcement of the existing concrete layer. Therefore, it is not given that under tensile load, they will reach the yield strength. Since the anchorage of the pull install connector is completely different from the behavior assumed by the Eurocode 2 design, it is actually necessary to assess their effect by a design method that consider the real anchorage behavior. That's why we have the TL66 method. And also that's why we are not using like the EC2 method, we are not using the yield strength of the connector or the bar um, as the factor. We're rather using the seals stress of the relevant failure mode, which is, for example, here in the TR66 design method, we will, the way we consider the sigma S, which is finding out the tensile resistance of the anchor of that relevant failure mode divided by the cross-sectional area. And here, the NRD, which is the resistance of the tensile resistance of the connector, we will need to consider many different failure mode. And according to the 66, there will be 9 failure mode. And here I'm showing you the 8 of them. They are actually very similar to what, if you familiar with the anchor design, it is actually very similar that we consider like the steel failure of the connector. We also consider the concrete failure in the newly casted concrete overlay section, like the concrete cone in new concrete, a pull out in new concrete, splitting in the new concrete. Also, at the same time, we also consider those concrete failure into the existing concrete layer. Again, concrete cone in the existing concrete, pull out in existing concrete, pull out plus concrete cone in existing concrete, or splitting in existing concrete. Here, we will have to consider the weakest link. We will need to analyze every single failure mode, trying to find out which is giving the lowest resistance, and then we put that lower resistance um, back to the formula to calculate the steel stress, the sigma s there. So that's why this is a bit the differences. I mean, when we compare to EC2, for EC2 design method for rebar, for semi-precast element, then they don't consider these kind of things. But here in tier 66, we have to consider that. So after we talk about that, and then let's move forward to talk about the second design flow, which is considering mainly in the edge area, or so-called along the parameters. And here we will have to consider the external forces and the restraint force due to strain gauge. So here, the ultimate goal is the verification of the first, the shear stress acting is equal or below the shear resistance. And also at the same time, we actually have to consider the tensile force acting into the shear connector is also equal or below the resistance. And here, I mean, it's mainly about the edge. And the way we calculate the width of the edge area, which is the LE, is really depending on the roughness of the surface. So the rougher the surface that is, then the narrower the edge area that is. So let's now focus on the part number one, which is again trying to verify the shear stress acting um, uh, is equal or below the resistance. So first, exactly the same formula that we consider on the first part, considering the external forces. Here we again convert the shear load into the shear stress acting. Here we use the same formula, but here what is the additional part, which is the 1b, which is we need to also calculate the resulting shear stress from restraint along the parameters. Again, so-called the cracking force. This is very straightforward formula that is being given in TL 66. It is like a tension resistance of the concrete. I mean, the maximum value that the concrete can take. So to calculate the tau ED, the resulting shear stress, you will need to define the LE. That's why that LE is again being mentioned here is depending on the roughness of the surface. Once that is defined, and actually you can also calculate these tau ED. Um, and here is important to remember that when we are comparing the tau ED to the tau LD, I mean comparing the stress acting to the resistance, here regarding the stress, we just need to pick one of them. They are not superimposed. I mean, so you're not adding 1A and 1B together. You're rather comparing and choosing the bigger one. So that later on then is being compared to the tau LD, the shear resistance that the system can take. And the tau LD, the formula here for parameter is actually the same like the like in the external force, which I show you the very long one is the same. So after we cover number one, the stress acting there, then also here we need to take care about the tension force acting there. Simply because just imagine when the top layer of concrete is having a strain gauge, this will actually create an uplifting force to try to uplift the connector. That's why here it's very important for us to compare um, that tensile force is below the resistance of the connector system. So the way to calculate the resulting uplift force here is again a very straightforward um, formula, as you can see here. It is mainly based on the concrete, the geometry, like the thickness of the new concrete overlay, time the width, time the design tensile strength of the concrete, divided by 6, and then you actually then can then calculate the resulting uplifting force. The way we verify here is by comparing these uplifting force to the tensile resistance of the connector. Here we will be repeating exactly, let's say that page, that slide that you have just seen, which is looking into those failure mode, and then we need to choose the minimum one, um, and then we compare. Going back to the previous line, we need to compare whether the NED, the uplifting force, is equal or smaller than the tensile resistance of the connector of the relevant failure mode or the weakest link. So that's a bit the formula as we discussed about. I mean, how you calculate the central area, for example, in a slab, which is only with the external forces, and also the way we calculate the parameters, which is the external force and the restraint force. And so what I'm going to share with you in this part is mainly how you can optimize your design. And one very important dimension is actually the interface roughness. This is the strongest, or this is a very strong influencing factor. So it actually requires a very careful preparation of the surface before the new concrete is poured. There are different methods commonly used. I mean, and depending on different method used, we will also achieve different roughness or different depth there. I mean, you can use let's say high pressure water jetting, sandblasting, or grating there. But I mean, actually, is yeah, I mean, the method is important, but more importantly is the execution. um, that's why here, I mean, on the left hand side, the picture showing you, if we use the same high pressure water jetting method with 1500 bar, actually the roughness, the R figure can be different. I mean, the one on the left hand side is a very good one, where the aggregate is fully exposed at 3.3 millimeters roughness, while on the right hand side is like the it's like a rough surface, but not as rough as the left hand side. So that's why, I mean, it's important that, I mean, we are not just only looking into the way to roughen the surface, but also we have to let's say specify the roughness, the R number, so that it is then when we later on show you, I mean, it will actually affect a lot on your calculation. So the way to measure the roughness, actually, I mean, the engineers or the inspector, they can do it is by pouring let's say certain amount of sand on the roughened surface and use these wooden spreader or wooden plate to spread it around in a circular way, and later on measure the mean diameter of of the circle, and later on put it back to the formula show on the top right corner. The R value is actually equal to 40 times V divided by the surface area of the sand. And then this is the way, this is the sand patch method according to Kaufman. And by doing so, then you can, let's say, check the roughness of the surface. And according to the Cook, there's like four type of roughness: very smooth, uh, which is something like, I mean, the freshly casted concrete on a steel formwork, they will be very smooth. And then you have another one which is smooth. You have the rough one, which is the R number equal or larger than 1.5 mil, and the very rough one is, and then again you see the aggregate is fully exposed and is larger than, I mean, the rough depth is larger than 3 mil there. The reason that we have to understand the roughness is because if we look back into that formula for from TR66 for pull install connector, when we calculate the shear resistance, the tau value here, the red one, I mean the one highlighted in red circle, they are the factor divided by TR66, and they are fully depending on the roughness of the interface. As you can see, for example, the CR there, the rougher the surface that is, then the better factor it will give. It is the same like the other K factor or the alpha factor. So that's why the rougher the surface that is, this is going to give you a positive uh, improvement or influence to your calculations. While the green one in the green color, which is product dependent. So that's why, I mean, this a factor you can find from the ETA, the European Technical Assessment of that product, according to this specific EAD for this TR66 design method. I mean, so by looking into that product ETA, you will be able to find out those alpha K1 or sigma or the FYK, the yield of the shear connector, that one. So this will also give you a positive influence to your calculation. Again, if the system or if the product you choose is that good. So this is the way you can look into to help you to choose, or let's say help you to optimize your design, either by going for very rough surface or by choosing a better products. And just a quick example here, I mean, one design we have seen before. Um, not going through every detail. What I just want to show you here is mainly the table on the right hand side. We are, in this case, we are using our screw anchor Hus3 M8, and depending on the roughness of the surface, actually uh, the number of connector per square meter change significantly if that is a very smooth surface. So the concrete interface is not helping. You will need, for example, 66 number of Hus screw per square meter. But then if you're using a very rough surface, you only need two of them. So that's why it's very important that you define the roughness, and so that you really optimize your calculations. Another questions that let's say a discussion I want to trigger here is always, I mean, when we're talking about the shear connector or the concrete overlay, we always heard there is a very simple, let's say, calculation method. It's like the formula shown on the top right corner. I mean, it's calculating the total area of steel connector. I mean, it's coming from the shear load divided by the yield strength of the connector, and then you see how many connector you need. But then the issue is here. Actually, such a design only considering the Dow effect of the connectors and actually neglect the interlocking or the shear frictions, which actually contribute a large part of the shear resistance. This will result in a very let's say unnecessarily high number of connector, too many hole to be drilled, too many chemical to be used. It is a very conservative design approach. I mean, a realistic design concept like the one we presented here can, for example, save up to 60% of the connector. So that's why, I mean, it's important to, let's say, now realize, I mean, TR66 is there, so you can use it for those calculations instead of using those rule of thumb, and doing a lot of, let's say, over engineering design there. So the last part is just want to quickly cover what is available from the Hilti side. So here, just want to show you two product that we have. Then let's start with the left hand side one, which is the Hus screw anchor Hus 4 14 time 130 with the use of the HCC 14 red plastic cap. I mean, once let's say you do your calculation, once you move to the job site, once the anchor is installed in the right positions, you can put the plastic cap on by hand. You can rotate the cap to any desired directions. I mean, the cap is very robust. It's good enough that the installer can walk on the assembled rebar mesh without damaging the cap. So then, I mean, this is one way you can, for example, carry out the concrete overlay installation by the mechanical screw. The other method, which is on the right hand side, which is the chemical method using the epoxy, the Hilti Heat LE500 V4 with the HCCB shear connector. And here, I mean, the shear connector itself is fully optimized shape that the head allowed to place the rebar in both directions. And the benefit is here. I mean, both system give you the flexibility to level all the shear connector to be the same level. So it is really flexible. And if we have to compare in a more detailed manner, probably I will focus on by the way, here I just also put in another system, which is the HCCK, like a headed bowl or headed rebar for the same type of applications. But I mean, for me, I mean, I'm mainly seeing either you're going for the Hus screw anchor or going for the HCCB. The reason is Hus screw is, I mean, really simple. Mechanical anchor, everyone more or less know how to use it. It the installation is very simple. It gives you the fastest way to install it, give you immediate loading, and also the installation complexity is very low because I mean you don't really need to clean the hole. You just mainly, I mean, you either let's say blow it out the dust or you use the drill bit. When you drill it, use the drill bit. Let's say bringing it up and down to clean the hole, then you can achieve the same performance. And here, the HAS4 is approved with for ETA static case or ETA seismic case. While for the HCCB, the reason is recommending that one is because I mean it can be used for ETA static, but also can be used for ETA fatigue. So whenever you're talking about fatigue design, actually this is the only solution that you can go for right now under the TR66 method. I mean, yes, the speed will not be as quick as, I mean, speed of installation will not be as quick as the hot screw because you are using the chemical anchor system. But still, I mean, it will give you some immediate loading like 1 kN. We put it here. But again, depending on your design requirement, if fact is a requirement, then this is really the option that is available. So these cover already, let's say, for today webinar. Thank you for joining. If you do have more questions regarding concrete overlay, yeah, feel free to put it in the chat box. We will take care at, let's say, by emailing you back the answer or following it up with you by our engineers. Or if you have a project that you have concrete overlay applications and you would need a design support, we can also support you in that sense because here, as you can see, the formula consider multiple factor and also different zone. So if you need to, let's say, get some design support, we can also do it. So please get in touch, I mean, to your local engineering office where then they can provide you the support you need. I mean, we have a few engineering team who are able to come and speak to you face to face regarding any design inquiry that you have. We also have a back office team who are available at the end of phone or through email. So I put all the details there. So feel free to let's say reach out to them. And also, if you want to know more, we have already several AskHilti article about concrete overlay being put into the platform. So feel free to go there and read some of them. We will continue to roll out a few more article and also hopefully after today's webinar, getting your feedback and see whether we want to arrange another let's say sections about overlay. It can be about the Hilti method on hook rebar. It can be about more design examples. So, but please do let us know what you want to hear from us so that we can bring it in the next webinar. So, um, being said that, so thank you a lot again for joining today's webinar. Hope you enjoy it and hope to see you again in the future webinar. So once you leave, you'll receive, I mean, let's say you can, by the way, already click the handout button to get these presentations. And yeah, so that's it on behalf of Hilti. Thank you again for joining us today. Have a great rest of the day. See you later. Bye.